Consider the function x squared minus 4x plus 3 on the interval 0 and 4. Let's verify that this function satisfies the three hypotheses of the Value theorem, and then we're going to use the theorem. Well, the first thing we need to check that f of x is continuous on the given interval, including the endpoints. The given function is a polynomial, and polynomials are continuous everywhere, and differentiable everywhere as well. So this parabola is continuous on 0 and 4, including endpoints. We also need to check that it is differentiable everywhere. Differentiable means it has a derivative everywhere. And it is true. The derivative of 2x minus 4, and the function is indeed differentiable on 0, 4, not including endpoints. After this, we need to check that f of 0 and f of 4 give you the same answer. That means we want the endpoints to have the same height at 0 and at 4. Well, at 0 we have 3, that's easy to calculate. And at 4 we have 4 times 4, 16, minus 4 times 4, which is 16, plus 3, that's also 3. So check mark, check mark, check mark. Let's use the Value theorem to find c such that the derivative at c is 0. So we're looking where the derivative is not positive and it's not negative, but 0. Well, for that, let's do step 1, find a derivative. The derivative for all x is x squared minus 4x plus 3 prime, which is 2x minus 4. Solve it when 2x minus 4 is 0. 2x is 4, x is 2. That means the Value theorem was not wrong, and it basically told us that there should be a root for the derivative, and we found that root. Not only that is the case, it also says that this c, which is 2, must be inside of the interval. It's on 0, 4, but not at the endpoints though. So indeed, 2 is between and 4, and that is the answer for C. For you to understand what did we just do and why this is important, I have a graph for you. This is the graph of y equals x squared minus 4x plus 3. We checked that at 0 and 4 we had the same height. We checked that this graph is continuous and differentiable on 0 and 4, but continuous should include the endpoints. Thus, there should be a time of x where the derivative is 0, and that has so many applications because the derivative equals to 0 quite often indicates minimum or maximum. So that's what we found. We found that the derivative at 2 is 0. That means that at 2 we have a critical point for this function, and it ended up to be global local minimum. So we don't want to look for those points if we necessarily don't know that they exist. That's waste of time. This theorem tells us that we can go ahead and look for points like this.